All right, here's our diagram of the Milne universe with time going this way and space, one dimension of space going this way. Um, the red lines represent Euclidean coordinates, and the green lines represent time, our coordinate time, Minkowski time, but it only it only represents the time for the central observer, because for the other observers, of course, the time would be slanted. Um, Now, this represents a light cone of all of the events that are currently being observed by this observer at the center. So what I'm going to do, or what I have done actually already, is to take these curved lines here and basically flatten them. And so the transformation involves taking x comma t to tau phi comma um, tau, where tau is equal to square root of t squared minus x squared, and phi is hyperbolic arctangent of x over t. And this only works in the domain where, let's see, negative x is less than t is less than positive x. And that is this basically the tips of those green lines. You can modify it a little bit, and what I've done is figured out a limit to this equation. And basically, it's imagining a line coming in here along that axis towards, this would be the line x, actually, x is x, t is 1, and x is approaching 1. So here is the limit of arctange of x over 1 as x approaches 1, and it comes out to be, oh wait, no, that comes out to be infinity. What I wanted to do was also take times tau, and I took the limit of x approaches 1, and I think I took actually divided by t inverse, tau inverse. And then we've got an expression that is the limit of infinity over infinity as x approaches 1, which we can use L'Hopital's rule for this, and it turns out that this limit approaches 0. So this becomes 0, 0 when you get close to, or when you bring this line over here, all of these points get mapped down to the origin. Now, I don't want to underemphasize that point. We took a mapping of an infinite number of events. See this green point, and this green point, and this green point, and this green point. All of those different green points are separate events. Yes, the space-time interval between any two of those events would be 0, and the space-time interval between any two of those events would be 0. However, the space-time interval between that event and that event would be a large number. That event and that event would be a large number. These are space-like separated events over on the edges. So it's only when a photon is traveling along a single direction, you get a zero space-time interval. And so taking all of those points that are on opposite sides of the universe and putting them at the origin means that this is not an isomorphism. So this model is materially different than Milne's model. Because in this model, when you look back into the past, you are literally seeing the point where the Big Bang erupted. In this model, when you look back into the past, you may be seeing phenomena that that were generated at the Big Bang, but then we're probably seeing them later. So you cannot actually see the Big Bang itself. There's no line of sight from here to the origin in this model. In this model, you literally see back to the origin. Okay, so though this is not an isomorphism, I did give the function a name, fold out. So the fold out function takes x comma t to tau phi comma phi, where tau is as I've previously defined them. The next step in this is a little bit of a simpler thing. This one takes, we're going to have tau phi comma phi taken to, we're going to apply a transformation. And you know what? I might as well put both of these functions on the screen right here. It's going to take that tau phi comma phi, and if the phi is 0, it'll map to x comma 0. So it'll give you tau phi comma 0. If t is not 0, it will give you x over t comma t, which is just tau comma phi. So that's what this mapping does. It maps it to tau comma phi. And what happens then is that we have the graph of the function with tau going this way. No. Yeah, with phi going this way, with the rapidity going this way, and the proper time going this way. Okay, and in the next step, what we want to do is stretch this cone so that instead of widening out like this, it ends up being a straight line. It's something they're calling conformal time, because for some reason they think that the speed of light should also operate as a constant in the tau phi variables. I don't think that was the theory in the first place, but we're going to go ahead and try to do that. But this is going to have some more complicated math in it, I think. Although last time I attempted this, I did not quite realize that this was just tau and phi here. So that might make it easier knowing that that's just tau and phi. So first goal is figuring out something that I'm going to call stretch y, and stretch y is going to be a function of x. So here's x equals -1, x equals positive, well, actually I don't know if those are what x equals -1 is, but this is x equals 0, and x is going up by regular increments on the way. Yeah, actually this is x equals 1, and this is x equals -1 right here. So what you can imagine is if I have a point here, then I need to stretch, first of all, I'm going to stretch this down to a point so that this becomes a straight line. And then this will be stretched by the same factor as that is. So if this length expands by a factor of 1.3, then this length should also expand by a factor of 1.3. So what we need to do is find out what that factor is. And to figure out what that factor is, basically I want to take this length here, which is 1 minus, you know what, I'm just going to use those variables that we figured out they were. This is tau right here. So this is 1 minus tau, this length here. 1 minus tau. And while I'm doing that, let's change these to phi equals 0, phi equals 1, phi equals negative 1. And so this distance here, or rather this distance here, we'll do this one. This is phi. This point is negative phi. And how do I want to work this? I want to make 1 minus tau times, you know what, rather than call it stretch tau, let's call it stretch, or stretch y, let's call it stretch tau. Stretch tau, because that's what we're really stretching, right? Stretch tau, comma, of times, and this is a function, stretch tau of phi. And we'll call that delta tau, which is 1 minus tau. 1 minus, actually I need a new variable. So let's erase that. I need a conformal time variable. That's the only new variable I think I need. So one of these, there's something called the curly eta, or curly upsilon, or there's an eta. I think one of those would be a good symbol for it. Okay, here's the curly upsilon from Mathematica. I think I'm going to use that one. It looks almost like an R, but it's kind of a cross between an R and a Y. But in order to make this line straight, delta upsilon has to be equal to the absolute value of phi. And depending on where we measure that from, because it's going to be kind of different, here we have a distinct point where this is exactly one unit of time after this point here at the origin. But when we apply this thing, the delta upsilon is going to be measured from here, and these points are going to be mapped to negative, are going to keep approaching that line asymptotically, and they're going to be mapped to a delta upsilon, a conformal time of negative infinity as we get further and further back. Which is kind of funny because there weren't that many of them before. These dots, there weren't an infinite number of these dots. These were constructed, well, I guess in some sense maybe they could be called an infinite number of dots because they cross an infinite number of observers. But oh well. I'm just gonna see if I can straighten that thing out and what needs to be coded. But let's go ahead and work with this thing. I'm just gonna call this stretch s tau of phi equals delta. I don't know how to write that yet, but that will do. Curly upsilon, delta upsilon, over 1 minus tau equals absolute value of phi over tau, right? So we need to start taking this phi and tau and looking at the events that we're talking about here. The phi is arctange of, what was it, x over t? And I've got everything in different variables now, so this is kind of helpful. And the tau is the square root of t squared minus x squared. Because this graph was labeled in x versus t, this graph is labeled in tau phi and going upward and phi going to the side. No, tau phi going this way and tau going up. And this one is labeled as tau going up and phi going to the right. So we're actually looking at these events along this line and these events along that line, and we need a description of those. These events are going to be x equals 1 minus t, I believe. 1 minus t comma t, with t going from basically going from 0.5 to 1. And the events over here are x equals you know what? Let me pull up my Mathematica code here of what I used for these. On this side, on the left-hand side, I used negative I comma 1 minus I, where I is a member of basically 0 to 0.5. And 0.5, I think, generated that point there. So no, I went in the opposite direction from 0.5 to 0. So let's put 0.5, 0. Because 0.5 was the green point. So it should be essentially that. On the other side, we got positive I comma 1 minus I, as I goes from 0 to 0.5. So let's switch this up a little bit. T equals 1 minus I. Then t minus 1 equals negative I. So this would be t minus 1 to t minus 1 comma t, as t goes from 0.5 to 1. And this one, t equals 1 minus I. So what is I? 1 minus t equals negative I. So t minus 1 equals I. Here, t goes from 1 minus 0.5 is 0.5, and 1 minus 0 is 1. And over here, t goes from 1 minus 0, which is 1, to 1 minus 0.5, which is 0.5. Okay, I just found an error here. I meant to subtract 1. T minus 1 equals negative I, and then 1 minus t equals I. So that would give us, instead of it will give us 1 minus t comma t over here, 1 minus t comma t. Okay, so that makes sense. The left-hand side is t minus 1 comma t, the right-hand side is 1 minus t comma t. And both of them have t going from 0.5 to 1. It doesn't matter what order those are in. That means for the left-hand side, this is going to be hyperbolic arctange of 1 minus t over t divided by square root of 1 minus t, or I'm sorry, t squared minus 1 minus t squared. Hand side. And for the other side, it'll just be hyperbolic arctangent 1 t minus 1 over t divided by square root of t squared minus t minus 1 squared. Run out of time. Thanks for watching.